Buddy. Today we're just going to talk about or taking the basic concepts of rotational motion and expanding on them a little bit. So you might remember over here some of our common kinematic equations. I know this is a little bit different. You can think about this as being initial and this as being final. Delta x being v initial plus 1/2 at squared. V final squared equals v initial squared plus 2 times acceleration times delta x. Well, it turns out, kind of realized this already, there's a lot of relationships between these things. For example, delta theta is a lot like delta x. Omega is a lot like velocity. Alpha is a lot like acceleration. And so literally, you can translate each of these equations into their rotational equivalents. So in this case, for example, this equation becomes omega final equals omega initial plus alpha times time. And this one becomes, instead of delta x, becomes delta theta equals omega initial times time plus 1/2 alpha t squared. And this one becomes this. And you might say, well, wait a second. Does it just work for these three equations? Sorry. Or does it work for everything? That should be final over here. The answer is it does work for everything. But before we get there real quick, I'm going to take us down a little historical side road. Let me quick explain. Before I get that, there is a brain break. You'll find it linked actually to the assignment sheet because this one will take a little bit longer. You place the numbers from 1 to 9 into this square so that each one of the rows and columns produce the result shown. Give it a shot if you get a chance. It's kind of fun. All right, here's the side road. Some of you know the historical context of the Rosetta Stone. What was so interesting about it? Well, it was part of building material for the Red Fort. But when it was dug up, people realized that it actually had 3 separate translations on it. Ancient Egyptian up on top in hieroglyphics, Demotic in between here, and then Greek down below. And they were parallel translations of the same passage. What was the significance? Well, every single high priest who ever had written hieroglyphics was now dead. Nobody knew how to read these hieroglyphics. What they needed was a primer to be able to figure this out. This was the piece that allowed them to actually figure out the parallel translation of the hieroglyphics using the Demotic in Greek. Once they had that starter, they could then translate most of the rest of the characters. Here's a close-up of it, just so you can sort of see it again. What am I going to do? We're going to make our own Rosetta Stone. But our parallel translation is going to be between linear motion and rotational motion. And you're like, great, Mr. Klammer, I don't see the use of this one. Well, just go with me for a moment. You'll see in just a second. So let's start with the basics. Displacement in linear motion is we use the variable x, and the unit we use is meters. Well, you already know this one over here. Angular displacement, we use theta, and we measure it in radians. You're like, okay, so these two are kind of equivalent to each other, just like in 2 different languages. Sort of like the Rosetta Stone we saw. The same thing you do with regular velocity measured in meters per second gets replaced with omega in radians per second as well. And acceleration A measured in meters per second becomes angular acceleration in radians per second squared. What about time? We haven't talked about this one yet. How does time translate? Well, this is interesting. It's one of the few that actually stays the same. Still measured with the variable t, still measured in seconds. Rotational inertia, we've hinted about already. It's capital I, and the units for it we haven't talked about at all are kilogram meter squared. We will spend a lot of time with that in the next unit. The same thing's true with torque. We've mentioned it, represented by the Greek letter tau, measured in Newton seconds. Again, more second semester. Regular momentum is equal to mass times velocity, and its units are kilogram meters over seconds. You're like, oh yeah, just did that one. Well, angular momentum, the variable is L, and the units are this. And you might say, whoa, L? Yeah, it's kind of unusual. What's the rotational equivalent of mass? Well, that's rotational inertia up here. And what's the rotational equivalent of v? Well, that's just the omega up here, angular velocity. And so literally, you can translate almost every single formula. Regular kinetic energy measured in joules, the formula 1/2 mv squared. There's also rotational kinetic energy, usually represented by RKE, also measured in joules. And we'll talk about what that equation looks like in just a moment, but you can sort of see the pattern. For each one of these, you can translate directly across this. And so all of the formulas you've learned up to this point, you can translate into their rotational equivalent. Let me show you some examples. So this formula, very quickly, all you gotta do, excuse me, is look on your Rosetta Stone and figure out, hey, what's the rotational equivalent of x? And what's the rotational equivalent of v? If you do that, you'll discover, hey, you can simply write this as this equation. Just substituting theta for x and omega for v. Same thing here. We'll just replace v with omega and a with alpha. This one, you're like, whoa, wow. Yeah, you could also write this one, delta x equals v0t plus 1/2 at squared, but we'll go the long way. You can rewrite as this. Theta, or x becomes theta, v becomes omega, a becomes alpha. T stays the same. This equation, the one without time, becomes this. Looks a little strange. You're like, wait, 3 Greek letters in a row, alpha, delta, theta. But yeah, it does work exactly the same. And regular kinetic energy, 1/2 mv squared, becomes rotational kinetic energy, 1/2 I, the equivalent of mass, times omega squared. And we already talked about momentum, just represented with capital L. This is angular momentum, one of the big conserved quantities. Now we're going to focus on these first ones here. We're going to save these along with torque and rotational inertia to our next unit. Well, interesting. One quick note on this one. How many of these formulas do they give you on the AP? Well, if you look down here, they give you 2, which are just the translations of those linear ones up there. You're like, wait, where are the rest of the ones? Well, they're not given, which means you're going to have to simply translate them. You're like, wait. Yeah, you can do it. You'll see like all these ones are here. You can translate them as necessary into the rotational equivalent. Could you please add a couple of things on the bottom of your sheet? You know already that theta is equal to arc length over the radius. Well, rearranging that, you can get arc length is equal to theta times radius. Likewise, you can do a little bit of work on this one, but I won't do it right now. You know that theta times r is equal to the distance. Velocity is distance over time. Well, if you look at this real quick, you could rewrite this as theta r, distance, over time. But you might recognize the fact that what is theta over time? Well, that's angular velocity. And so you can actually calculate the velocity of a point on a rotating object just by taking omega times the radius of how far it is away from that point. Please realize they don't all have the same linear velocity. It depends on what the r is for each point. Likewise, you can do the same thing here. Acceleration is normally velocity over time. If you use omega r over time, you know that omega over time, the change in omega or change in time, is alpha, the angular acceleration. You might ask, why are these little t's on here? These t's stand for tangential. Why? We'll go a little bit more detail later, but these are motions that are tangent to the motion of a rotating object. If you think about the velocity of a bicycle wheel, a point on its edge is going to be moving this direction. And so the velocity is a tangent to the circle or tangent to the radius for an object moving in a circular path. So we put little t's down here to indicate these are, even though we're talking about circular motion, these are tangential velocities, tangential accelerations. Put these in the bottom of your physics Rosetta Stone as well. Now, some quick examples of how you actually use these formulas now. So take a look at this one. A pottery wheel is accelerated uniformly from rest to a rate of 10 revolutions per minute in 30 seconds. First of all, we got to convert revolutions per second into something a little more convenient. So doing that, 10 revolutions, each revolution is 2 pi, so I kind of cheated here. 10 times 2 pi, that's the number of radians 10 revolutions is equivalent to. And 1 minute, 60 seconds. And if you simply divide that, you end up with pi over 3 radians per second. I'm going to leave it as a radical, I know. You're like, or not as a radical, but with the pi in it. And now we can look at this. What was the wheel's angular acceleration? Well, you remember regular good old angular acceleration is just a change in omega over change in time. And because it started from rest, delta omega is just going to be the final velocity over the time it took, 30 seconds. And so we get our angular acceleration as pi over 90. And now B. How many revolutions did that wheel undergo during that time? And you're like, whoa, 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 how do I solve that? Well, just like learning a new language, the first time you're going to face this, you're going to think about, hey, how would I do this if I knew regular acceleration and I knew time and I knew the final velocity and I'm looking for revolutions, which is sort of like distance. And you might say, oh, yeah. Delta x equals v0t plus 1/2 at squared, or written out long ways. Well, we need the rotational equivalent of that formula to solve this one. And so if we use this one, just the direct translation of this using the Rosetta Stone, we can actually solve it. And so plugging in our numbers, plugging in initial omega, 30, our acceleration, which is pi over 90, and our time, which is 30 seconds. The time is 30 seconds. That's not initial omega. Initial omega is 0. We can actually solve this. And I don't know why I have that twice. But you can realize it comes out to 5 pi radians, or they want revolutions. Remember, there are 2 pi radians in each revolution. So taking 5 pi divided by 2 pi gives us 2.5 revolutions. Likewise, you can do it with this one. Now, I want you to start slowing down just a little bit. This is like an initial velocity. This is like acceleration. And we're trying to find time, t. And we're trying to figure out how long it's going to take to stop. So we're looking at time. That's supposed to be a question mark. And we've got initial velocity, we have acceleration, and we know the final velocity is going to be 0. And hopefully you would say, oh, wait. I'd use this equation. Yeah, good. And so what we're going to do is use the rotational equivalent of that, which looks like this, and plug in our numbers. And we get our time. Same way here, think about, all right, if we had time of acceleration and we have initial velocity, how would we solve for delta x? And again, you should say, oh, yeah, we'd use that one because we have acceleration in time. But we'd use the rotational equivalent of that, this one, and just plug in our numbers. And you get the answer. This is a lot like learning a new language. The first time you're working with a new language, what do? You hear it. You translate, say, for example, a question in another language into your language, answer it in your language, and then translate it back into the language you're trying to learn. Right now, we're doing this kind of the hard way. I'm saying doing this first. At some point, you're going to get comfortable enough, you won't have to do this first, and you can jump right to the rotational equivalent or equations and solve it. But it takes a little while. Think about this as foreign language day 1. Take a look at this one. A coin of radius 1.5 centimeters initially rolling within a rotational speed of that and comes to a rest after experiencing an acceleration of this. Again, this is sort of our final velocity, the equivalent of it. This is sort of our acceleration, angular acceleration. And this is our initial velocity. and you're thinking, all right, we're trying to find angle. Again, this is sort of like delta x. Notice that we don't have time. You should immediately go, oh, whoa, 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 wait a second. Yeah, it'd be that equation, but use the rotational equivalent of it, because that's what we're working with at this point. Plugging in our numbers, you can get theta. Through what linear distance the coin travel? That one's a little trickier. We're going to go back to the definition of radians. You're like, wow, yeah. Or you could use S equals theta r that we had a few slides ago. And just plug in our numbers and find out that the arc length the coin would go through, or the distance it's going to travel, 1.35 meters. One final example on this one before we get going. We've got RPMs, so first of all, we got to translate that into radians per second. So that many revolutions, each revolution's 2 pi, 1 minute, 60 seconds. And you can very quickly then get to the angular velocity in radians per second. What angle did it go through? Most of you at this point would be saying, oh, we don't have time, but we do have all these units, so we can just solve it by plugging in this. Sorry, it's a little tight here. Plugging in our numbers, this is our acceleration from up above. We can solve for delta theta, which is fairly large. And then last question on this one, for what distance did it move? Again, just using this, we can figure out it moves about 81.8 meters. I'll leave this one for you to try on your own, although tonight you have a couple of homework questions that relate to this as well. Calvin and Hobbes was a cartoon from a while back, but this is interesting. Calvin, the child here, if you don't know this story already, always gets into all sorts of mischief, and usually the father is the one ripping out his hair. In this case, though, it's actually the kind of reverse. Talking about a vinyl record, talking about the fact that even though they both go around once in the same time, they have to move at 2 different speeds because the outside piece has to be covering a greater distance in the same amount of time. And Dad's all happy he explained it. Meanwhile, Calvin can't sleep at night. He's stuck awake all night thinking about it, like, wait, how is this possible? Sorry, I just had to put a little comic relief in. There's a brain break in here. I'll let you try it later. I'm not going to give you the answer in this one because it gives it away. You can figure it out as well. We'll go through it later if you want. But coming back to the equation we've talked about before, this is the one I sort of showed you briefly before. This allows you to find the velocity of an object that's moving along a path. So when it's at this point, its velocity is that way. When it's at this point, its velocity would be somewhere along this point. And it's moving through some distance as it does that. If the tangential velocity is changing, in other words, if it's speeding up going from here to here, we have tangential acceleration, which we've already talked about looks like this. So imagine you had this red ball here moving with this initial tangential velocity, and a brief moment later, it speeds up, and now it's moving faster over here. This involves something, or not only is it undergoing angular acceleration, it's also undergoing tangential acceleration. Its angular velocity is increasing, and so is its regular. It has both. Yeah, it's kind of fun. But interesting enough, again, the units for this, and I should have pointed out before, are radians. Oh my goodness, radians over second squared. And when we multiply that by r, which is in meters, and some of you see already what's coming, you get the units for tangential acceleration, which are going to be meters per second squared. And you're like, whoa, 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 wait a second. What happened to radians? Again, remember that they don't exist. And then take a quick look at one example problem on here. We have to do a little bit of conversion here real quick. You know what? I'm going to skip this one just for speed, because I want to get into this most important topic today. The Rosetta Stone is useful in a lot of ways, but it's time for something new. This is a bizarre idea. And here's the biggest idea from this section of the chapter. And by the way, this is the sort of big start of the second section. An object traveling in a circular path, even if it's moving at a constant speed, is accelerating. And you're like, what? Wait a second. You're like, wait, no. Acceleration is how much the velocity changes over time. If it's moving at a constant speed, there's no acceleration because velocity isn't changing. Well, we've kind of skirted this before, but remember that velocity is a vector. And there's two ways that you can change a vector. You can either change its magnitude, make it bigger, make it smaller, or you can change its direction. And if you look at this animation over here that I put in, notice that the velocity, even though it's a constant in magnitude, is constantly changing in direction. And because velocity is a vector quantity, changing its direction is a change in the velocity. And so this is a new type of acceleration due to the change in the direction of the velocity, not its magnitude. And so we're giving this a new name. We're calling it centripetal. And don't panic too much on this one, but what's going on here? Centripetal means center seeking. And this is a little bit hard to understand, but I'll prove it to you in just a moment. How much does, or what is the direction of delta V when an object's moving in a circular path? So here's V initial and here's V final. If I'm trying to find delta V is always the final minus the initial. But in this case, I'm going to cheat a little bit and write it as V final plus negative V initial. Well, if you look up here, V final is this vector pointing down this way. Sorry, I kind of draw it here. And so I'm going to draw it down here, and then I'm going to add to it negative V0. Well, V0 is pointing up this way. Negative V0 is the exact same length, but pointing down this way. So the sum of these two gives us delta V. And so what direction is delta V pointing? Straight down, which means the centripetal acceleration also has to be pointing straight down towards the center of the circle. And this is that new type of acceleration, which we're going to call centripetal acceleration, center-seeking acceleration. You're like, great, we know what direction it points. This new acceleration points towards the center of the circle. But how do we calculate this magnitude mathematically? This is, all this geometry stuff. Well, give me just a moment here. And I'm going to take you through a little bit more geometry first before we get there. Take a look at this. Here's an object that's traveling around a circle with some velocity v. And the velocity you could actually express, it would be equal to the circumference of the circle, 2 pi r, divided by the time it takes to go around once, which would be v, or capital T, the period. Blah. But what happens as it moves around? Well, here's the velocity a brief while later. Now, I'm going to do a different trick to find delta v this time. It turns out, if you've got these two vectors here and you draw them tail to tail, so here's my blue vector, here's my red vector, blue vector, red vector, this little part right here actually gives me delta v. And now I can continue this around the circle. So a little bit later, it's moving with that velocity. I can find delta v for that. And now over here, that, and then here, that. And then I could do it for all the other points, and I'd get something that would look like this. And some of you might have guessed already, wait a second. If you drew in every single possible tangential velocity at this point, filled this all in, it would fill in this part as well, and we'd actually end up with a full circle. Think about it. The more points I put in here, the closer this would become to a perfect circle. In fact, if I put this in all the way around here, all these arrows would end up approach a polynomial with more and more sides until finally it would approach a perfect circle. Well, the total delta v, as it went around once, would be the total length of this circumference of this circle. Now, be careful. What is the circumference of this circle? In other words, what is delta v in red here? Well, if you think about it, delta v is the circumference of the circle 2 pi times the radius, but the radius of the circle is v, the velocity vector we got from over here. I know it's a little bit bizarre, just hang tight. You're like, whoa, wait a second. And so finding the acceleration, it's the change in the velocity. In this case, we're looking at the change in the magnitude of the velocity, or sorry, change in the direction of the velocity, not its magnitude, over the time it takes, which gives us this. And here it is, our first equation, which actually tells us what is the acceleration due to the change in the direction. You can just take 2 pi times the velocity of the object divided by its period that it takes to go around once. That one's interesting, but there's actually a couple more useful formulas to derive. Remember that velocity is equal to this, based on what we just talked about. Well, we can plug that in over here, and it looks ugly, but it reduces to simply this. And this equation is actually quite useful to find centripetal acceleration. Just 2 pi times the radius of the circle over the period squared. And now, next slide, forgive me for a second, we've got these two equations. For no reason whatsoever, I'm going to take this velocity equation and square both sides. And you're like, what? Wait, why in the world did you do that? Well, trust me for a second. Look at this piece right here, and look at this piece right here. They're very, very similar, except for one small detail. Can you see it? Yeah, it's this squared part right here. In fact, all I need to do to make them equal to each other is divide both sides of this equation by r. And so I get this. Now, remember your transitive math stuff? If centripetal acceleration is equal to this, and this is equal to v squared over r, then that also has to equal to v squared over r. And, and you can also do a little bit of work on this one real quick. Remember, tangential velocity is equal to v times r, omega times r. And if you plug that in for that velocity, you can get this equation. So here it is. You have 3 equations for centripetal acceleration, or 4, for centripetal acceleration. Which is the right one? The answer is all of them are. Which one do you choose? The one that's most convenient. If you know velocity and period, use the first one. If you know radius and period, second one. Velocity and radius, the third one. Omega and radius, the fourth one. All right.
The moon is always falling, yet it stays in the sky. The gravitational force from the Earth makes the moon accelerate according to F equals ma. Although it continues to accelerate all of the time, it moves at nearly constant speed. This seems to contradict the very concept of acceleration. But acceleration is the rate of change of velocity, and velocity is a vector. The speed is only its length. A body can be accelerated even if its speed is constant, provided its direction changes. This point becomes clearer with the introduction of another concept, the derivative of a vector.
Don't worry about that, just think about change.
The derivative of a function explains how fast it's changing at any given instant. The derivative of a vector explains how fast the vector is changing. A vector can change by changing its size, or its direction, or both. The change in a vector is itself a vector.
Delta x, or
the vector, v, although it's always perpendicular to r, is itself undergoing uniform circular motion.
Change in velocity, delta v, over time.
Its derivative is the acceleration.
We're doing limits here if you haven't realized it.
That solves the puzzle of constant acceleration at constant speed. As a body undergoes uniform circular motion, the acceleration continually redirects the velocity vector, which continually redirects the radius vector. They all keep in step with each other, constant in magnitude, but changing continually in direction. The idea of the derivative of a vector is not as new as it may seem. Remember, F equals ma is itself an equation about the derivatives of vectors. The only difference is that previously, by taking derivatives one component at a time, only ordinary functions have been differentiated.
In uniform circular motion, the velocity is perpendicular to the radius vector, and the acceleration is perpendicular to the velocity vector. So it points along the radius vector, but in the opposite direction.
And I'll stop it there, but you can sort of see it. That's that inward acceleration. I just wanted you to see the graphics so you could sort of visualize a little bit easier, although derivatives of vectors a little bit intense. So one quick note on this one, centripetal force. If I could change one thing about your physics textbooks, I would remove this term. Why? This seems like a new force. And we'll talk more about that in a second. But what is centripetal force? Centripetal force is the net force required to keep an object moving in a circular path. And it's simply equal to the mass of the object times the centripetal acceleration. So centripetal acceleration, just a sub c, one of these four equations. To find the centripetal force, we just multiply by the mass of the object that's going or traveling in that circular path. We usually write centripetal force as F sub c for force centripetal. And remember, it always points towards the center of the circle. What's my pet peeve about this one? Centripetal force is just the name that we give the net force required to keep an object moving a circular path. It is not a new force. This net inward force can be created by one or more of our four forces we've talked about already: gravity, normal force, tension, or friction. It's not a new one, which is why I wish they'd simply called this net inward force instead of centripetal force, because it just confuses students. So for example, you can have gravity that produces that net inward force. It can be the normal force. In this case, the force of the track on this train keeps it moving in a circular path. It can be tension. For this hammer throw, it's the tension in the steel cable that's producing the net inward force. Or in this case, this cars, as they're drifting around this track, it's the force of friction between the tires and the road that allows them to keep it. And it's a little bit, not quite enough for these that are doing the little slide here. It can also be a combination. For example, here, it can be the force of gravity on the cars along with the track pushing down, a normal force. Depending on how the speed, you might need more than one force to keep it moving in the circular path. And so, again, just a quick reminder, F sub c just stands for the net inward force that keeps an object moving, and it is provided by one or more of the following. How do you find it? Find the centripetal acceleration using one of our formulas, multiplied by the mass, gives you the centripetal force. And yeah, just a quick reminder about all these. You can look at it again. And then you get to our lab. And I'll actually perhaps skip that for a moment and hop over here and take a quick look at a centripetal force example. In this case, this is a bird's eye view. What you have here is a 1,000-kilogram car going around a circular track at 30 meters per second. And let's say it's going this direction. What is the force that keeps it going in a circular path? Well, we need a net inward force. And the thing that's going to produce that force is actually the force of friction. Between the tires and the car, technically static friction. Whoops, that's interesting. How would we figure out what force is required? First thing we do is find the centripetal acceleration. And if you remember the formulas there, in this case we have velocity and radius, so probably do v squared over r. And our centripetal acceleration this time, 30 squared over 50 should give us, if I did my math right, 18 meters per second squared. So what's the centripetal force need to be? Centripetal force, again, remember, is just the centripetal acceleration times the mass, ma. So in this case, what's the force required? It's just going to be 18 times 1,000, or 18,000 newtons. And that force has to be directed to the center. And what's going to be producing that force? It's got to be this force of friction that's doing that, either as static friction or perhaps kinetic if they're kind of drifting around the curve. Hopefully not. And yeah, there'd be a force of gravity and a normal force pointing out of here, but I just want to show you this piece. What about this one? So you've got a ball, a 1 kilogram ball going in a vertical circle. Again, we have radius and velocity. First thing I'm going to do is solve for the centripetal acceleration, is v squared over r. And in this case, that's going to be 5 squared over 2, or 12.5 meters per second squared. And now here, this is where it gets a little interesting and where I want to stop today. What in the world then is the centripetal force? We're like, oh, that's easy. Mass is 1 kilogram times the centripetal acceleration. We need a net force of 12.5 newtons. Now remember, this is the net force. So when it's at the bottom, let's make gravity 10. You've got the force of gravity acting downward on it, which is already 10 newtons. Remember what centripetal force is. It's the net inward force. So here's my question. What does the tension need to be on our ball when it's at the bottom of our loop so that the net inward force can be 12.5? That force has to be directed towards the center. You're like, oh, that's easy, 12.5. Not quite. Why? This has got to be the net force. We already have the force of gravity down this way. What does the tension have to be in this case? Well, it has to be 12.5 newtons larger than the force of gravity. It has to be 22.5 newtons. And then what about when it's at the top? Well, when it's at the top, it already has the force of gravity acting downward on it. Force of gravity is going to be 10 newtons. What does the tension have to be at the top? You're like, oh, we did that already. It's 22.5. No, not quite. The tension doesn't have to be as large here as it is at the bottom. Why? Gravity's already sort of helping us. What's the tension have to be in this point? I drew it too large. It only needs to be 2.5 newtons. Again, the sum of these two produce that net inward force, 12.5, that I need. All right. With this, you should be able to do most, if not all, of your homework questions. I just want to see the next slide here. Oh, yeah, actually, let me do... No, you should be fine.